Mr. Cursey here. Now I'll be going over the solutions to the 2022 paper in some detail. So since this is a fairly long video, I've created headings for each question in the timeline below the video so that you can easily find the particular solution you're interested in. You should see the question numbers as you slide along the timeline. So let's begin the solutions. So here's question 1. We have 2/3, and that's outside brackets which contain an addition of two fractions. Now I think maybe to try and understand the order of how we do things, suppose it was just plain forward whole numbers. Then we would do what's in the bracket first to get 4, and the 2 outside the brackets means a multiplication, so it would be 2 times 4, which would give us 8. So we must do the thing in the brackets first. So we're looking at 1/5 plus 3/4. And we must get the denominators being the same. After all, there's different ways of writing a fifth. We could double the top and bottom. We could multiply top and bottom by 3. We could multiply top and bottom by 4 and by 5 and so on. All sorts of different ways of writing 1/5. Similarly for 3/4, we could double top and bottom. We could multiply top and bottom by 3, multiply top and bottom by 4, and so on. And if we look at all these different equivalent ways of writing these fractions, we can see that there's one way for writing a fifth and a way for writing 3/4 that has the same denominator. We're talking now in 20ths, and this one's 4/20, and that's 15/20. So we should be able then to add them. So 2/3, and remember outside the brackets means we're going to multiply. 1/5 we're multiplying top and bottom by 4 to get 4/20, and we're multiplying top and bottom of 3/4 by 5 to get 15/20. So we're now able to look inside the brackets and say, well, if we've got 4/20 and we're adding another 15/20, 4 of them plus 15 of them gives us 19/20. And we're now left with 2 fractions to multiply. Now in the case of a simpler one where we try to work out a half of a half, we know a half of a half's 1/4. And how we get there, we multiply the 2 numerators, 1 times 1 is 1, and multiply the 2 denominators, 2 times 2 is 4. So we'd multiply the 2 times the 19 to get the numerator, and we'd multiply the 3 and the 20 together to get the denominator. Now at this stage, just as we multiplied top and bottom by 2, 1/5 to get 2/10, we could have divided top and bottom by 2 to get 1 and 5. So we're allowed to divide top and bottom of these fractions by the same number. So we could divide by 2, that goes once, and we could divide this 20 by 2, that goes 10. So in effect we've cancelled 2 from the top and the bottom of the fraction, and we're left with 1 times 19. On the bottom of the fraction we've got 3 times 10, that's 30. And there's no more cancelling that we can do in this fraction. So that means it's in its simplest form. All common factors have been cancelled out between the top number and the bottom number. So there we go, the answer is 19/30. So let's move on now to question 2. So here we have a function f of x equals x cubed minus 2, and we have to evaluate that function when x is -3. Now, just by way of explanation, some people like to think of a function as a machine mysterious box where we don't know what's quite inside it. This box in this particular case is labelled F, and then there's a wee entrance where numbers can be put in, and there's a wee exit where a corresponding number will come out. So this number eating machine, if you like, it processes a number. If a 1 goes in, something comes out. It might well be -1. And the way we say this or write this down is F with 1 going into that function machine and -1 appearing out of it. For instance, we might put 2 in and out would come 6. And we'd say that by F, 2 goes into the function F, and 6 comes out. So in this case, the secret of what goes on inside there, what is done to these numbers inside the box, that in this case is given by this formula x cubed minus 2. And the secret in this case is when a number goes in, 1 for instance, then that number is cubed and 2 is taken away. So in the case of 1, we've got 1 times 1 times 1, there's 1 cubed, and 2 is taken away. Now 1 cubed is 1, take away 2 from that, you get -1. In the case of 2 going in, 2 cubed, 2 times 2 times 2 is 8, and then we take away 2 from that and we get the number 6. So that is how this number-eating machine called F, the function F, how it works. It's using this formula x cubed minus 2. So if x goes into this function machine, this number-eating machine, then out comes x cubed minus 2. So in the case we're asked to evaluate, these are all the values of the function. When we put in 1 to the function f, the value of that function is -1. So we've evaluated the function when x is 1 and the value is -1. We've evaluated it. So we're asked to evaluate this function when x is -3, when we put in the number -3 into that, what then comes out of this number-eating machine, number processing machine. So we have to apply this formula. -3 goes in, we first of all cube -3. So we've got -3 times -3 times -3, and once we've cubed that, it tells us to take 2 away. That's just how we treated the 1, how we treated the 2 to get the -1 and the 6. So -3 times -3 is +9. 9 times -3 is -27. And then we have to take 2 away from that. And it's not -25, it's -29. If you remember a number line, if you're at -27 and you're taking away a number, you're going this way. It's like if you're taking away from 0 and you take away 2, you'll get to -2. So if we're taking away 2 from -27, we're ending up with -29. So we've evaluated this function f when x is -3, and we've got the value of -29. Question 3. We've got a diagram showing a cone. We're given a couple of measurements in that cone, and we're asked to calculate the volume of the cone. Now they say pi is 3.14. That's what we have to use anyway. We know pi is not exactly 3.14, but we have to use that since we've no access to calculators. So at the front of your exam paper, you discover this formula. Volume of a cone and we're told on the formula sheet that the volume of a cone is 1/3 pi r squared h. So we now have to identify all these missing letters and find their values and then do the calculation. So first of all, r, well, we know pi, we're supposed to use 3.14. r is the radius of this base. Now we're given the diameter, that's from this edge to this edge, and you should know that the radius is 1/2 of that diameter, and you can see that that's 10 centimetres. Couple of radii end to end will make up the diameter. Diameter is twice the radius. So there's the first thing, the radius is 10 centimetres, and this obviously is the height of the cone, so that will give us the value of h. So I think we've now got everything we need to put in the missing values. So we've got 1/3, we've got pi, which we're told to use 3.14, we've got the radius, we know is 10 centimetres, and we have to square that, so there'll be 10 times 10, that's 10 squared, and then we have to multiply by the height, which is 60. Now first of all, let's look at the third and the 60. We'll use these two first. And 1/3 of 60, if we divide 60 by 3, we get 20. After all, 20 and 20 and 20 makes up 60. 20 is 1/3 of 60. So that's that. We've still got 3.14 to use. Now 10 times 10 is 100. And we know multiplying a decimal like 3.14 by 100 that in effect the decimal point moves 2 places to the right. The 3 units column will become a hundreds column. So 314 uses up the times 100. And therefore we have to multiply 314 by 20. Well, if we multiply by the 10 and then by the 2, 10 times this be 3,140, and therefore we have to double 3,140. So doubling each of these, or doubling 314 gives you 628 with the 0 at the end. For the 10, remember 20 is 2 times 10, so what I've done is multiplied this by 10 and then doubled the answer, used that and then this. So we end up with 6,280. Now it's a volume. Volumes are measured in little cubes. Everything's in centimetres here, so it must be centimetres cubed for that. So let's just check we've answered the question, calculate the volume of the cone, and we've done what they've told us, use 3.14. We've not to change it to litres or anything like that. So there's our final answer, 6,280 centimetres cubed. So here we have question 4. We have a tangent AB, we have a diameter CD, and C is the point of contact of this tangent to the circle. We've got the size given of angle EOD. Now remember, O is the centre of the circle. And you can see it lies in that diameter CD. So the size of EOD is given as 68 degrees, and we're asked to calculate the size of angle ACE. Let's just highlight that in red. There's the angle we're trying to find. Now there's two parts to this angle. You can see there's this yellow part on the left and there's a blue part. So if we concentrate first of all on finding the size of the yellow part of this angle ACE, I think we'd be making some progress. Now, you'll notice that this yellow part is formed from the tangent, and a radius, that's from the centre out to the point of contact. Now the size of that angle, therefore, will be a right angle. It will be 90 degrees. So that's the yellow part. Let's have a look at the blue part of the angle. Now it sits in this triangle OCE. Now it's not any old triangle. It's a very special triangle because one vertex is at this origin, the centre of the circle, and it consists of two radii. The side OC is a radius, goes from the centre out to the circumference, and OE is also a radius, it goes from the centre out to the circumference. So let's just highlight that. These two purple lines, they're both radii, and we know that radii of a circle are always the same length. Now that immediately tells us that this triangle is isosceles. Two of the sides are equal, and therefore two of the angles are equal. This angle over here must be the same size as this angle. So there's progress. We've got an isosceles triangle, and we've got this blue angle being the size of this blue angle. They're both equal. Now in this triangle OCE that we're working on, this third angle COE is part of a straight angle COD. Now let's look a bit more closely at that. That red angle is the third angle in the triangle. Let's just move this radius round. You can see there's the straight angle. It's now all red. Obviously adds up to 180 degrees. So the red and the green always add up to 180 degrees. And here's another special case when both the angles are right angles and the radius is perpendicular. And then we can move that radius all the way down, and the straight angle is now completely green. So we have 68 degrees plus this angle here being 180 degrees. So that angle will be 112 degrees. We take 68 away from 180, we get 112 degrees. So let's put that in here. It's 112 degrees. Now, the final piece of the puzzle comes from realizing that the three angles in this triangle add up to 180. So we've got 112 degrees plus the two blue angles give us 180. But we've already worked out, or we already know, that 68 degrees added to 112 degrees gives you 180 degrees. So these two blue angles must add up to 68 degrees, which means each of them must be half of that. Because they were equal, each of them must be 34 degrees. You can just check that 34 plus the 34 gives us 68. 68 plus the 112 gives us 180 degrees, which is the angle sum for the three angles in a triangle. So we now have enough to give us the required angle. So the required angle will be the sum of these two parts, the yellow and the blue. So remember, the yellow was a right angle, it's 90 degrees, and the blue we've now worked out is 34 degrees. So we have 124 degrees as the size of angle ACE, that red angle that we highlighted before. So here we have question 5a. We're asked to express this quadratic expression in a particular form. And the form we're asked to express it in has a x plus a all squared term in it. Now, let's look at a typical example. Suppose it was x plus 7 squared. Now that means x plus 7 times x plus 7. And we know to multiply out this, we'd use firsts, outsides, insides last. You may have your own method, but most people would know the firsts. That's x times x, first two terms multiplied. And the outside two, 7x, and the inside two, 7x. And then the last, 7 times 7. And there we get a typical quadratic expression. There's 14x there. And we'll notice that that 14x compared to this 7 is half of 14. Now that 14x comes from two terms, a 7x and a 7x, and that comes from the outside two terms and the inside two terms. And they're each the same because it's a squared expression, x plus 7, x plus 7, identical terms. So the outside and inside terms will both be identical. So in particular, when we're looking at x squared plus 8x plus 15, the x terms, there's 8 of them, they must surely come therefore from an x plus 4. So let's just explore that and see if we're right. And if we're multiplying out x plus 4 times x plus 4, the first two terms, the first terms in each bracket, x squared, the outside two terms, x times 4, the inside two terms, 4 times x, and the last two terms, 16. So we're ending up with x squared plus 8x plus 16, which is pretty close to what we were after. So it would look like that x squared plus 8x plus 15 can be written as x plus 4 all squared, but not quite. That 16 has to be a 15. Well, that's easily dealt with. We just take 1 away from it. And now you can see that we do have it in this form where a is 4, and well, there's a wee technicality, but b would be -1. We're adding -1 for b, and we know that adding -1 is just the same as -1. So basically, x squared plus 8x plus 15 we've written in the required form as x plus 4 all squared minus 1. So now let's look at part B. And we're now asked hence or otherwise. Hence would imply we're using the answer that we've just worked out. Hence or otherwise state the coordinates of the turning point of the graph of this function f of x equals x squared plus 8x plus 15. So we're basically looking at the graph of f of x equals x plus 4 all squared minus 1, and trying to determine where the turning point of that graph is. So let's do an exploration of turning points on graphs. So here we have the graph of y equals x squared. Now how we read this, when x is 0, 0 squared is 0, so there's a height of 0 on this graph above the x-axis. When x is 1, 1 squared is 1, so the graph is now at a height of 1 above the x-axis. Here's x equals 2, 2 squared is 4, so the graph goes up to a height of 4 above the x-axis. So the heights of the graph are telling you the values of x squared. For negative values, -1 squared is +1, -2 squared is +4. That's why the graph symmetrical about the y-axis. So the minimum turning point is down here. So the turning point occurs in this graph where the value of x squared is at a minimum, and the smallest value that something squared can take is 0. Now let's have a look at what happens when we change to x minus 1 squared. Now you'll notice that the minimum point has moved 1 to the right. Why is that? Well, at this point x is 1. If we put 1 into this expression x minus 1, 1 minus 1 is 0, and that's when we get the minimum value of this squared term. When x is 1, we've got a 0 squared. When x is 2, 2 minus 1 is 1, 1 squared is 1 again. And when x is 3, 3 minus 1 gives us 2, 2 squared is 4, so we're up to 4, and so on. If x was negative 1, for instance, negative 1 and another negative 1 is negative 2. Negative 2 squared gives you positive 4. So in effect, the whole graph has been shifted 1 unit to the right when we subtract 1 from x. And similarly, if we subtract 2 from x, it'll have moved 2 units to the right. Remember, initially it was at the minimum turning point was at x equals 0, and subtracting 2 has moved it 2 units to the right. And again, when x is 2, if we put 2 in there, 2 minus 2 is 0, so we get its minimum value of 0 squared when x is 2. And if we have x minus 3 all squared, minimum value is at x equals 3, and x equals 4, minimum value, 4 minus 4 is 0, 0 squared. So when we subtract numbers, the graph, original graph, the x squared graph, is moved to the right. You can imagine what happens if we add numbers. In this case, when we put x equals negative 1 in here, negative 1 plus 1 is 0, so we're back to 0 squared. It has its minimum value when x is negative 1. So if we're adding numbers to x, the original x squared graph has been shifted to the left. There's x plus 2, it's moved 2 units to the left from where it used to be. And there's x equal x plus 3 all squared, x plus 4 all squared. And you'll notice that x plus 4 all squared is part of the expression we're trying to find where the minimum or the turning value of the graph is. So we're nearly there. However, there is another aspect to this. Let's look at x squared plus 1. Now in this case, all heights have been increased by 1. Instead of 0 squared, we've got 0 squared plus 1 for the minimum. So when we add 1, the whole graph shifts up by 1. We're increasing the height of every point in the graph by 1. There's x squared plus 2, x squared plus 3. X squared minus 1, x squared minus 2, and so on. Now the graph, we're trying to find the minimum value, or the coordinates of the minimum turning point. Well, we didn't know it was a minimum, we do now, is x plus 4 all squared minus 1. Now you'll see when x is negative 4, the squared term is at its minimum of 0, and because of this negative 1, this minus 1 at the end, we've reduced the height by 1, so it's now down at a height of negative 1. So this turning point on the graph is negative 4, negative 1. So back to the question, we can now say that the turning point occurs, and we've seen it happens when x is negative 4, and that ensures we've got a 0 squared. It's at its minimum there when x equals negative 4, and that'll obviously, when this is 0, we've got the y coordinate of negative 1. You remember that from the graph. So the turning point occurs when x is -4 and y equals -1. So the coordinates are -4, -1 for the turning point, which happens to be a minimum turning point of the graph. So here's question 6. We're asked to find the equation of the line passing through these 2 points, and we have to give that equation in its simplest form. So a couple of methods I'm going to show you. First method, well, just to refer to the points, let's call the first one -3, -1, and the second one -5, 7pq. Probably good to do a little graph just to see roughly what the picture's like. -3, -1. There's the point P. And the point Q, -5, 7. And we join these up. And of course that line extends in both directions. So there's a picture of that line. You'll notice a downhill line, fairly steep, so be a negative gradient, quite a large number. So how do we work this out? So we need to know, well, the first method anyway, we need to know 2 things to find out that equation. The first thing is its gradient, and traditionally we call that m. Second thing we need to know is a point on the line, and we'll call that a, b. And if we know these 2 things, the gradient and a point on the line, then we know the equation of the line, because there's a formula for that. The equation of the line in this case is y minus b equals mx minus a. So that's y minus the y coordinate equals the gradient times x minus the x coordinate. So that's the formula we're going to use. Now, to find the gradient of the line joining P to Q, it's the y difference over the x difference. Now, if we start with the second point for the difference, the y difference, the 2 y coordinates, 7 minus -1, if we start with that second point, we mustn't swap the order around. We must start with this second point when we do the x difference, which would be the difference between the 2 x coordinates. That's -5 minus -3. So there's your y difference over your x difference. So 7 minus -1, 7 plus 1, which is 8. And -5 minus -3 is -5 plus 3. And if you're on your number line, -5 plus 3 will take you to -2. And that gives us -4 for the gradient. Now that ties in nicely with this picture, where if you go along 1, you've gone down 4, along 1, down 4, and so on. So that gradient is okay, and if we'll use a point on the line, well, either of these were spoiled for choice. We could use -3, -1. Let's choose that one. And the equation therefore, that's using your y minus b equals mx minus a, is y minus the y coordinate, that's the -1, equals the gradient, that's -4, and x minus the x coordinate, which is -3. A lot of brackets in there. Take away -1 is +1. -4, and inside the brackets here we're taking away -3, so that's +3. So we've got y plus 1 equals Let's multiply this out. Negative 4x, and negative 4 times 3 is negative 12. We can still simplify this a bit by subtracting 1 from both sides. So we get negative 4x, and if we subtract 1 from negative 12, we get negative 13, not negative 11. So there's the equation, y equals negative 4x minus 13. Now that's one method. Let's have a look at method 2. So in method 2, we'll suppose the equation is y equals mx plus c. Now, the gradient, we can certainly work it out just like that, and it's negative 4. I won't do the same calculation again, but the gradient's negative 4. Another way we could do that is looking at this graph and say, well, look, we can make up a wee triangle here where to go from Q along to P, we have to go along this distance. Now that's from negative 5 to negative 3. That's a distance of 2. And then we're going down, height of 7, down to a height of negative 1. So that'll be 8 down. So remember, gradient's the distance up or down divided by the distance along. So that'd be 8 over 2, but negative because we're going downhill. So it's negative 8 over 2. That's negative 4 as before. So we've got m being negative 4. So we know that y equals negative 4x plus c is the equation. We'll now use one of the points. Let's use negative 5, 7. It lies on the line, so its coordinates, x and y, must satisfy this equation. So in this case, we have to put in x equals negative 5 and y equals 7 into this equation. So 7, that's your y, equals negative 4 times x. In this case it's negative 5 we're putting in, plus c, and c is the constant at the end that we don't know as of just now. So what have we got? We've got 7 equals, now negative 4 times negative 5 is positive 20. And if we take 20 from both sides, 7 minus 20 is equal to c. So c is negative 13. So finally the equation is y equals negative 4x, and we've just found out that this constant c is negative 13. So it's negative 4x minus 13 as before. So here's question 7. We're asked to change the subject of this formula to b. So let's write the formula down. D is equal to, and then we have a fraction, and the top of the fraction is the expression b plus 4. On the bottom of the fraction we have c squared, but similar to 2 equals 8 divided by 4, for instance. Now when we're changing the subject of the formula to b, we're trying to get b on its own. We get a formula that has b as the subject. This formula has d as its subject. It's d on its own equals, and then there's a big formula involving b and c. In this case, b would be equal to, and there'll be a formula here that involves c and d. So we have to attempt to get b isolated on its own. So the first thing we'll do is to attack the divide by c squared. It's like in this one, this divide by 4. For instance, if we were to do the opposite of dividing by 4, if we multiplied by 4, then that would get rid of that 4. The 4 and this 4 would cancel out, and we'd be left with 8. But obviously 2 is not equal to 8. We'd also have to multiply the left-hand side by 4. So that therefore would produce 4 times 2 being, and this cancels with this, would get 8, which is, you can't really argue with 4 times 2 being equal to 8. So we had to do the same to both sides. In this case, the divide by c squared, to undo that, would be multiplying the right-hand side by c squared. And if we're doing that to the right-hand side, to balance it, we would have to multiply the left-hand side by c squared. Just like when we multiplied the right-hand side by 4 here, we had to balance it by multiplying the left-hand side by 4. Otherwise, the two sides would not be equal. So doing this, the c squared vanishes and we're just left with the b plus 4, just like the 4's vanished and we were left with the top of the fraction 8. So we're left with the b plus 4. And on the left-hand side, we've multiplied d by c squared. So there's c squared times d, c squared times d. Now we can leave out the multiplication. C squared times d can be written as c squared d. So we've reached this stage. Now, still b is not on its own. We have a plus 4 in the way. So a similar sort of situation would be 5 equals 1 plus 4, and we're trying to get rid of that plus 4. And we would, on the right-hand side, we could take that 4 away, but we'd also have to take the 4 away on the left-hand side. In this case, these would disappear. We'd be left with a 1. 5 minus 4 is the same as 1. Don't think you'll argue with that either. But we had to do the minus 4 to both sides. So in this case, we want rid of this add 4. So we do the opposite. We subtract 4, take away 4. And if we do it to the right-hand side, we also do it to the left-hand side. So what do we end up with? So on the left-hand side, we had c squared d, and we've to take away 4. On the right-hand side, taking away the 4, that makes the adding 4 disappear, because that was the whole purpose of taking away 4, and we're left with just the b on its own. Now we're almost there. Normally, formulae don't have the single letter on the right-hand side, so we just swap the order round. b is equal to c squared d minus 4, and that is a healthy formula where b is the subject of the formula, just as we were asked to do. So here we have question 8. We're shown part of a graph, and we're told the formula for this graph, y equals a sine bx degrees. And we're asked to, in part A, to state the value of this number at the front, the A, not the number in front of the angle, B. Now, it would be interesting just to see the effects, get a general feeling for the effects of A and B on the graph. So let's do that now. So here we have a normal sine graph, 0 up to 1, down to 0, negative 1, back up to 0. By the time the angles reach 360. Its amplitude is 1. It reaches a height of 1 and down to a negative 1 for its minimum. So that's the amplitude. And then its period is 360. It has one complete cycle every 360 degrees. Now let's have a quick feel for what these A and B numbers do. A is at the front, in front of the sine, and B is in front of the angle. So if we increase A, you can see that that's affecting the amplitude. And then if we increase B, you can see that's affecting the period. So that gives you a feel for what these A and B numbers are doing. So now if we look at the question graph, you'll notice it has an amplitude of 3, goes up to a height of 3 and a minimum value of -3. So its amplitude is 3. Now since the amplitude of a normal sine curve is 1, we might suspect that the value of A therefore will be 3 times 1. So A is 3. Let's go back to the graph and check that. So let's move the value of A up to 3. And as you can see, it comes up to a maximum of 3 and a minimum of -3. So there's an amplitude of 3, and we have a 3 for the value of A, the number at the front of the sine. So let's look now at part B, where we're asked to state the value of B. And remember B, the number in front of the angle, that affected the period of the graph. So we'll go back to the sine graph and look in more detail at how B affects the period. So here's the normal sine graph again, and you'll notice that between 0 and 360, one complete cycle. That's when there's a 1 in front of the angle X. So let's increase the value of B from 1 to 2. How's that affected the period? Well, we've now got 2 complete cycles when we go from 0 to 360 degrees. The period's been halved. The period's now 180. But there's now 2 cycles where we used to have 1. And the number B is 2. Let's increase it again up to 3 this time. And count the cycles. There's 1, there's 2, there's 3. So where we used to have 1 cycle, we've now got 3 cycles. And the value of B is 3. So it looks like B tells you the number of cycles between 0 and 360. Let's go back to the question. And looking at the graph in the question, we can see there's 1 complete cycle between 0 and 45. So the question now arises is how many cycles are there between 0 and 360? In other words, how many 45s make up 360? Well, let's have a little diagram. There's 4 right angles make up 360 degrees. Each right angle can be divided up into 2 45-degree angles. There's 1, 2, 3, 4, 5, 6, 7, 8 lots of 45 degrees make up 360 degrees. So it would appear that possibly this number is going to be 8, and then we'll get 8 cycles between 0 and 360. Well, let's check that up. So we want to increase the value of B to 8 and see how many cycles that produces. There we go. There's 360 degrees. Basically, we're wanting to know if this is 45 degrees. Well, there's 1, 2 in the first 90. Another 2 cycles takes us up to 180. Another 2 cycles takes us up to 270. And another 2 cycles takes us up to 360. So it appears we've got our 8 cycles and that this is indeed 45 degrees. Now, we should be able to extend this axis and we'll now have a graph that's a bit closer to the one in the question. There's 90 degrees, halfway between 0 and 90 is 45. So this is 45 degrees, and remember we had to have an amplitude of 3. There we go. And we've now got a pretty close match, or a perfect match actually, to the graph that's shown in the question. It's got an amplitude of 3 and it has a complete cycle between 0 and 45 degrees. So let's go back to the question finally, and we can finally say therefore that the value of A is 3, that's the amplitude, and this graph is 3, and the value of B is 8, since it's a sine graph that'll have 8 cycles between 0 and 360. Got a period of 45 degrees. It's an eighth of 360 degrees. So here we have question 9. Triangle ABC, we're told the lengths of the 3 sides, and we're asked to calculate the value of cosine of B. Now that would imply the cosine rule. Now remember, in this paper, paper 1, you don't have access to a calculator. So at the front of your exam paper, you'll be told this version of the cosine rule, 2 versions of the cosine rule, and it'll be the second one that we're looking at, where there's a cosine of A, B squared plus C squared minus A squared over 2BC. But this one has cosine of B, so we really have to change the roles of the A, B's and C's here. Cosine of B, now you'll notice in this version, cosine of A, we've got the other 2 letters, not A, that's B and C to begin with, so the other 2 letters, not B, would be A squared plus C squared, minus, and we've got little a squared, capital A, there's capital B, so we'll have little b squared. And then in the bottom of the fraction, twice BC, same as these 2 letters. So this will be twice AC. So there's the version we're going to use. And as a reminder, these little letters A, B and C, on this diagram, little a always occurs as the length of the side opposite angle big A. So that's little a, and there's angle B, a large capital B. Opposite that, we'd use little b for the length of that side, and then opposite angle C, side little c. So in this case, we know now the values. A is 3, B is 5, and C is 7. And we have to substitute these values into the formula. So that means therefore that cosine of B will be equal to 3 squared plus 7 squared minus 5 squared, and that answer divided by twice A times C. So all I've done is substituted the values of the letters for the values we were given. So let's calculate this. 3 squared, 3 3s are 9, 7 squared is 49, 7 7s, and we have to subtract 25 from that. The bottom line, 2 3s are 6, 6 7s are 42, and we've got 49 plus 9 is 58, so we're subtracting 25 from 58. We should get 33. And it said in simplified form, in simplest form, there is a common factor. 3 goes into 33 11 times, and 3 goes in 42 14 times. So once these have been cancelled, divide top and bottom by 3, we get the fraction 11/14 as the value of cos B. And this is question 10, where Tommy's out buying flower seeds from a website. Well, he wouldn't be out, he'll be doing that from his home. But he's given a 30% discount and he pays £16.10p for the seeds. We have to calculate what the flowers would have cost, the seeds would have cost without a discount. In other words, we're after 100%. We want to know what 100% of the price is. See, with this 30% discount, he gets 30% off. In other words, he's only paying 70% of the full price. That's what a 30% discount would mean. So we can equate 70% or match up 70% with what he pays. That's £16.10. Now, one of the ways of finding out 100% would be to first of all find what 1% would be. Now, if we know 70% is this, 1% will be 1/70th. We'll divide by 70. It doesn't matter what this comes to, we just write it down just now. Divide that by 70. We'll sort that out soon. So we now know what 1% of the full price is. We're after the whole full price. That's 100% of it. Now, if we know 1%, we can find 100% by multiplying by 100. It's 100 times the cost of 1%. So it's whatever this nonsense is times 100. Now that's the calculation we have to do. So let's do that. If we're multiplying by 100, it's the top line. Remember, it's 100 over 1 multiplying fractions. Multiply the top two numbers. So it's 16.10 times 100. That'll be 1,610. And on the bottom, we've got 70. Now, immediately we can divide top and bottom by 10. It's not a problem. And we do a little division. So we need to find out how many times 7 goes into 161. Remember, paper 1, no calculators. So 7 into 16 is 2. 2 sevens are 14. That leaves a remainder of 2. And 7 into 21 goes 3. 3 sevens are 21. So we've got 23. So we know now, therefore, that the full price without a discount is £23. There are ways of checking this. We could check if this is the correct answer, then let's work out what a discount of 30% is. That's 30 hundredths or 3/10. If we divide, let's multiply 23 by 3, that'll be what, 69, and divide it by 10, we'll get 6.9. So there's a discount, £6.90. So presumably if we have £23, or no, let's add it on, if he pays £16.10p, he's got a discount of hopefully £6.90. So if we add these two values together, 90 plus 10 is £1. So 16 and 6 is 22, plus the £1 is 23. So we certainly have full price of 23. So all this checks, and the full price seems to be £23. So here we have a indices problem. We're asked to simplify this expression, m to the negative 2 to the power negative 2, and that is raised to the power 4. We've then to multiply the result by m to the negative 5. So let's tackle this letter raised to a power raised to another power. Let's look at an example. Suppose we had, let's take m, since that's what we're using. Let's take m squared cubed. And what do we do with these two indices? Well, let's see what m squared cubed means. It means we take m squared and cube that. In other words, multiply it by itself 3 times. And we know that m squared is just m times m. and that's happening 3 times. So if we count the number of m's that we're multiplying together, we get 6 of them. And I think you can now see what we've to do with these indices. We've to multiply them. So m to the negative 2 raised to the power 4, we would multiply these two indices. So we get negative 2 times 4, which would be negative 8. Now multiplying two powers, suppose we had m squared times m cubed, and a couple of m's, and there's 3 m's multiplied. And counting them all up, we get m to the power 5. So what have we done to these two indices? We've added them. So in this case, we add these indices. Negative 8 plus negative 5 is negative 13. Now, that's all good and well, but we're supposed to give an answer with a positive power. And the last thing we have to remember is that negative powers, for instance, m to the negative 1 is 1 over m. M to the 1, or m to the negative 2 is 1 over m squared. That's what negative powers mean. So their final step here, 1 over m to the power positive 13. And that's the answer written with a positive power. And here we have question 12. It's an algebraic fraction question. We're asked to express this division of two fractions as a single fraction in its simplest form. So we have the first fraction, 4 divided by x plus 2, and that's to be divided by 5 over x plus 2 whole squared. So that's our division, two fractions. Now I'll show you two ways of doing this, one the usual conventional way and one a slightly more unconventional way. So in the conventional way, you have to remember that when you divide by a fraction, it's the same as multiplying by the inverted fraction. In other words, you take the first fraction, leave it as it is, and instead of dividing by this second fraction, you multiply by the inverted fraction. You turn it upside down and multiply. So to divide, turn upside down and multiply. So there's what we've now got. So fractions, remember, you're multiplying the top two numbers together and you're multiplying the bottom two numbers together. 5 times x plus 2, that would be written like this. Now we can look at the top and bottom of this fraction. Remember, x plus 2 squared means x plus 2 times x plus 2. And we can divide the top and the bottom of this fraction by x plus 2. There's a factor of x plus 2 in both top and bottom. For instance, if we had 24 over 20, for instance, we can write the top as 2 times 3 times 4. And we can write the bottom number as 4 times 5, sorry. There you go, 5 times 4. And you'll notice that this factor of 4 occurs both in the top and the bottom of the fraction. So we can divide the top number by 4 and divide the bottom number by 4 to get 6 over 5. In other words, that's what's happening when we cancel out the factor, a common factor of 4 top and bottom numbers. So this factor of x plus 2, we can divide the top line by that, and we can divide the bottom line by that. And what are we left with? We're left with 4 lots of x plus 2 over 5 lots of 1. So we have 4 times x plus 2 over 5. And that's a single fraction in its simplest form. So we'll call that method 1. It's probably the method most used. Let's have a look at method 2. Slightly unorthodox method, but I think this method has more understanding in it, but nevertheless let's go ahead with it. So we've got a couple of fractions divided. So we have this fraction 4 over x plus 2, and it's being divided by 5 over x plus 2 all squared. So we end up with double-decker fraction, if you like. And you know, in fractions we're allowed to multiply top and bottom by the same number. And let's see what happens to get rid of this divide by x plus 2. We're trying to get rid of the double-decker nature of this. So we would multiply by a factor of x plus 2, and that would cancel with this to get rid of it. You can't do that to a fraction without balancing it by doing the same on the bottom line. So we've immediately got this x plus 2 cancelling one of these x plus 2s. We'd need another one, because there's an x plus 2 times an x plus 2 down here to get rid of. And I can't multiply the bottom of this fraction by another x plus 2 unless I do that on the top of the fraction. So I've got this double-decker fraction, and I'm multiplying top and bottom by x plus 2 times x plus 2. Now, why am I doing that? That disappears, cancels out, and both of these, the x plus 2 squared, cancels with these. What have I got left? Well, on the top line I've got 4 times x plus 2, and on the bottom line everything's gone bar the 5. And there is the same answer as before. Now, whichever method you fancy, that's up to yourself. Use the method you're most comfortable with. Oh, here we have question 13, a third question. We have to expand and simplify this third expression. So let's write it down, get used to it. So outside of brackets we have a square root of 10. Inside the brackets we've got square root of 10 minus the square root of 2. So it's similar to 3 lots of x plus y, where you would multiply out 3x plus 3y, that type of thing. And we've also got a plus 8 root 5. So first thing, let's do this multiplying out. Root 10 times root 10. Now the basic definition of the square root of a is a number multiplied by itself gives you a. Square root of 4 is 2 times the square root of 4 is 2. 2 2's are 4. So the square root of a number times the square root of the same number will give you that number. So root 10 times root 10 will give you 10. Root 10 times root 2, there's something we're going to have a look at in a second. And we've still to add 8 root 5. Now notice that root 10 is not multiplying the 8 root 5. The root 10's domain is just everything that's in this bracket. So there we go. So we've got 10 minus. Now there's several ways of dealing with root 10 times root 2. One of the methods is to say, well, okay, we can take both of these numbers under the square root sign to get 10 times 2, square root of 20. Simplifying the square root of 20, we know 20 can be written as 4 times 5. I'm choosing to write it that way because I do know the square root of 4 is an exact number. A whole number. Square root of 4 is 2. So 2 times root 5, we write that as 2 root 5. So that would be one method of tackling this. Another method, root 10 times root 2, we can split 10 up into 2 times 5, or 5 times 2. Now why would I do that? Well, I would do that because look what we end up with, a root 2 times a root 2, and we know what root 2 times root 2 is. It's just the number 2. Well, root 5 times 2, that's normally written as 2 root 5, in the same way that, say, 3 times x is written as 3x, or x times 3 is also written as 3x. So root 5 times 2, 2 root 5, either way. And there's also an 8 root 5 to be added. Now, interesting, this comparison with x's here, if we had a minus 2x plus an 8x, how would you simplify that? You'd say, oh, that's 8x minus 2x, that's just 6x. Well, similar way, we've got 8 root 5s and we have to take away 2 root 5s. We'll have 6 root 5s. That basically is all you can do with it. We've expanded it and simplified it. The final answer is 10 plus 6 lots of root 5. And here's question 14. We're asked to sketch a graph. And there it is, y equals the formula, y equals x plus 1 times x minus 3. And we have to use the axes below. On our sketch, we're supposed to show clearly the points of intersection with the x-axis, the y-axis, and the coordinates of the turning point. Now, the first thing to consider is what kind of a graph are we going to be looking at. And we know that if we multiply out an expression like x plus 1 times x minus 3, firsts give us x squared, the outside 2 negative 3x, the inside 2 1x, that will be minus 2x, and the last 1 times negative 3 is negative 3. And we're therefore looking at a quadratic expression, and therefore it's going to be a parabola. And because it's got a positive x squared term, it's going to be concave upwards. It's going to be shaped that way, not upside down, if you know what I mean. So that's what we're expecting. So let's tackle and turn the x-axis followed by the y-axis and then the turning point. So for points on the x-axis, what do we know about every point on the x-axis? It has a height of 0. The y-coordinate is 0. Now, if we take this formula that we're given for this graph, then we can substitute y equals 0. So we have x plus 1 times x minus 3 equals 0. And we have a good old quadratic equation. It happens to be factorised. Something times something equals 0. Therefore, one or other of these must be 0. They both could be 0. X plus 1 equals 0, or x minus 3 equals 0. If x plus 1 was 0, then x would be negative 1. If x minus 3 is 0, then x is 3. And we've therefore got the points of intersection with the x-axis. One of them's at negative 1, 0, and the other one is at 3, 0. So we're going to have a curve going something like this. But let's just fill in another detail for points on the y-axis. And what do we know about them? For points on the y-axis, this time the x-coordinate will be 0. And if x equals 0, let's plug that into the formula for the graph. That's just replacing x by 0 wherever it occurs. Then we've got y equals 1 times negative 3. so y equals -3. So we now know that the graph must cross at 0, -3. So that's the y-intercept, if you like. There's the two x-intercepts, there's the y-intercept. Now we're probably at a stage where we can sketch in the graph. The only other thing to consider, and this gets us on to the last one, is that parabolas have axes of symmetry, and they pass through, in this case, the minimum turning point. So where would that axis of symmetry be? The gap between -1 and 3 is a distance of 4. Half of that's 2. So if we go 2 to the right from -1, we'll end up at 1. If we come back 2 from 3, we'll end up at 1. So there's the axis of symmetry. Its equation, we're not asked for this, but its equation is x equals 1. So we sketch in a curve which comes down to a minimum and back up, that's supposed to be symmetric. So there's my parabola, and we're asked for the coordinates of the turning point. Now we know the x-coordinate is 1, but we're not sure of the y-coordinate. So the final step of working is, when x equals 1, let's plug 1 into the formula. We get 1 plus 1 times 1 minus 3. So y is equal to 2 times, this comes to be -2, so that's -4. So the minimum value on this graph is -4, and the turning point is at 1, -4. So I better state that, turning point 1, -4. And we've annotated the graph clearly enough, -1, 0 and 3, 0. And 0, -3. All the intercepts have been labelled. So I think we've done enough to earn our marks for this question. So here's question 15, part A. We're given a diagram of a triangle and of a rectangle, and we're given dimensions. And some of these dimensions involve a variable x. So first of all, we're asked to find an expression for the area of the triangle. Now, areas of triangle, one of the ways of finding that area is to take a half of the base length times the height, half base times height. So in this case, it's a half of the base is 3, and a height, well, it's an expression involving the variable x. It's x plus 12. Now I'm going to write a half of 3 not as 1.5, but as 3 over 2. And that's outside, or multiplying the bracket with x plus 12 in it. Now there's the expression. The units when we find area will be square centimetres. So there's part A. Let's move on to part B. We're told that the area of this triangle is equal to the area of the rectangle, and we have to find algebraically the value of the variable x. So part B involves, first of all, finding the area of the rectangle. And again, we've got a good old formula that we're familiar with. It's length times breadth. Now in this case, let's choose the length to be 6. Choose, I mean, you can't alter it, but it could have been 8 minus x. And the breadth will, if we've chosen this as the length, the breadth will be 8 minus x. So easiest way of writing that is just 6 lots of 8 minus x without the multiplication sign. And again, square centimetres. Now we're told these two areas are equal. So we know that 3 over 2 times x plus 12 is equal to 6 lots of 8 minus x. These two values must be the same. Now, why I've written this as 3 divided by 2, it's easier to double both sides. We're in an equation, so we do the same to both sides. Double both sides. That'll get rid of this divide by 2, and we'll be left with 3 lots of x plus 12. If we've doubled the left-hand side, we must double the right-hand side. We've got 6 lots of 8 minus x. We'll now have 12 lots of 8 minus x. And that brings to mind the fact that there's a factor of 3 in common on both sides. We could take a third of both sides, divide both sides by 3. If we've got 3 lots of x plus 12 and we divide by 3, we'll have 1 lot of x plus 12. So that 3 times will disappear. Now if we've got 12 lots of 8 minus x and we divide by 3, we'll be left with 4 lots of 8 minus x. So the right hand side deserves multiplying out. 4 8s are 32, and remember 4 times the x, we're taking away 4 lots of x. Don't forget to multiply the second term by the 4 also. What shall we do? I think possibly we'll add 4x to both sides. X plus 4x would be 5x. Still got that plus 12, still got the 32, and adding 4x to this side, the negative for the minus 4x vanishes. Oh, we're getting there. We'll subtract 12 from both sides. That plus 12 disappears, and 32 minus 12 is 20. And final stage, divide both sides by 5 to get 4. Now let's read the question. Find algebraically the value of x. And we've found that x is 4. Now at this stage it may well be worthwhile checking. If we look at this triangle and we know x is 4, the area of that triangle will be a half times 3 times, we now know the height is 16. 4 plus 12, that's 16. And what will that be? A half of 16 is 8, 3 8s are 24. So that's 24 square centimetres for the area of the triangle. Let's look at this rectangle. It was 6 times 8 minus x. Now x is 4, 8 minus 4 is 4. So that'll now be 6 times 4, which again is 24. So there's a wee check that indeed both the areas are the same when x is 4. So we do have the correct answer. Well, that's Mr. Carsey signing out, and hope you enjoyed the video.